You've probably heard that the Earth is over 4.5 billion years old, and that an asteroid or meteoroid collided with Earth around 66 million years ago, and that humans evolved as many as 300,000 years ago. But where do these numbers come from? How do scientists calculate them? And are they reliable? In historical geology, there are two approaches to dealing with time. The first approach is called relative dating. It is the science of determining the relative order of past events, such as the deposition, erosion, intrusion, and faulting of rocks. Because it is relative dating, you are only focused on the order. Which event came first? Which came second, third, fourth, and so forth. In this way, relative dating will tell you the sequence of events, but not when those events actually happened. Absolute dating is the science of assigning a numerical age to an event, telling us how long ago it actually happened. Obviously, we can't date an event itself, but we can determine the ages of minerals, rocks, and even fossils that provide evidence of the event. Relative dating and absolute dating are not done in isolation. As you will see, each approach has its advantages and disadvantages. It would be ideal if we could assign a numerical date to each and every mineral, rock, or fossil. But not all samples are suitable for absolute dating methods. And even if they were, absolute dating is a costly and time-consuming process. In comparison, relative dating is fast and inexpensive, even if it doesn't give you numerical dates. That said, scientists don't have to pick one approach over the other. They can do both. Scientists are usually quite happy to have both the relative sequence of events as well as their absolute ages. Knowing the age of certain rocks can make a world of difference for a geologist. They don't need to have an age for every sample, just a few important ones. So, how do scientists determine these ages? Absolute dating is also called radioactive or radiometric dating because it relies on the process of radioactive decay. Recall that all matter in the universe, everything that has mass and takes up space, consists of atoms, and that the atoms themselves consist of three types of subatomic particles: positively charged protons, negatively charged electrons, and neutral neutrons. Neutrons and protons make up the nuclei, or the centers of the atoms, and the electrons occur in a cloud around the nuclei, orbiting them like planets around the sun. There are many types of atoms, called elements. Each element has a unique number of protons, its atomic number. Because elements are ideally neutral in charge, they tend to have the same number of electrons. Hydrogen, the lightest element, for example, has the atomic number 1 because it has one proton in its nucleus and one electron orbiting it. Carbon, the most important element for life, on the other hand, has 6 protons and 6 electrons. But that's not the end of the story on elements, because although each element has only one unique number of protons, the number of neutrons is not fixed. When an element has atoms with different numbers of neutrons, we refer to those atoms as isotopes. Again, we will look at hydrogen and carbon. Hydrogen has three isotopes: protium, deuterium, and tritium. Protium has no neutrons. Deuterium has 2, and tritium has 3. But as you can see, the numbers of protons and electrons are fixed. Overwhelmingly, protium is the most common isotope of hydrogen. Deuterium and tritium are far less common in nature. Unlike hydrogen, there are 15 known isotopes of carbon. But only 3 of these isotopes occur in nature: carbon-12, carbon-13, and carbon-14. We designate these isotopes based on their atomic mass, the number of protons plus neutrons. Carbon-12, for example, has 6 protons and 6 neutrons. Its atomic mass is 12. Most atoms of carbon are carbon-12 isotopes. Carbon-13 and carbon-14 isotopes are comparatively rare, making up a little over 1% of all carbon atoms. Let's stick with carbon-14. Although it is the rarest of carbon isotopes, it is the most important for absolute dating, because it is the only radioactive isotope of carbon. A radioactive isotope is an atom that contains an unstable combination of neutrons and protons, meaning that the arrangement has an excess of energy. The only way for radioactive isotopes to become stable is to shed this energy and mass through a process known as radioactive decay. There are 3 different pathways of radioactive decay. In each pathway, an unstable radioactive parent isotope is replaced by a stable daughter isotope along with some other form of energy and mass. We can call these byproducts alpha, beta, and gamma particles. Alpha particles are positively charged helium nuclei. Beta particles are negatively charged electrons. And gamma particles are light particles called photons. The details of these pathways aren't super important. You can do absolute dating in historical geology without them. The most important thing to remember is that the parent and daughter isotopes are usually 2 different elements. In the case of carbon-14, the parent isotope undergoes beta decay, producing the daughter isotope nitrogen-14 and beta particles. Carbon-14 becomes nitrogen-14, carbon to nitrogen. Of course, carbon-14 is not the only radioactive isotope, and it certainly isn't the only important one for historical geology either. There are many unstable isotopes, and they all undergo some process of radioactive decay. This radioactive decay doesn't happen right away. Even though the parent isotope is unstable, it may exist for thousands, millions, even billions of years before spontaneously decaying. On an atom-by-atom basis, radioactive decay is a random process. You can't predict when it will happen for any given atom. However, if you look at all isotopes of a kind, you will find that they have a tendency to decay after a certain period of time, known as its half-life. The half-life of an isotope is the average time it takes for half of the parent isotope atoms within a sample to decay and become daughter isotopes. This graph helps visualize the meaning of half-life. The horizontal axis is the number of half-lives, and the vertical axis is the fraction or percentage of all parent isotopes represented. Over time, these isotopes will either decay or remain in their unstable state. As you can see, at time 0, all of the isotopes remain unstable. After one half-life, half, or 50% of the atoms have decayed, and the remaining half, or 50%, remain unstable. After two half-lives, 70% of the isotopes have decayed, and only 25% remain unstable. In nature, it is virtually impossible to find a sample with no radioactive isotopes. Atoms are just too numerous. There are always bound to be some radioactive isotopes in low concentrations. But after 5 half-lives or so, the number becomes insignificant. How long does a half-life last in terms of actual years? The duration of a half-life depends on the radioactive isotope. Some isotopes, like samarium-147, are a little unstable, and their half-lives are really, really long. Indeed, the half-life of samarium-147 is 106 billion years. That's more than 7 times the age of the universe. It takes a really long time for samarium-147 to disappear after it's created. Carbon-14, on the other hand, is highly unstable. Its half-life is 5,370 years. It disappears much quicker than samarium-147. So what can we actually date with radioactive isotopes, and how? You can analyze the concentrations of parent and daughter isotopes in just about anything using an instrument called a mass spectrometer, or mass spec. There are many different types of mass specs. What's most important is not understanding how to analyze, but what to analyze. In historical geology, you can analyze rocks, minerals, sediment, or fossils. And beyond historical geology, the sky is the limit. You can acquire data on just about anything. But for the best results, you ideally want to analyze samples which acquired all of their radioactive isotopes at the time of their formation and did not gain or lose any of the parent or daughter isotopes over time. Let's consider a few examples to help explore this idea. Let's think about some of the best samples for radiometric dating. One of the most important minerals in absolute dating is called zircon. It consists of zirconium, silicon, and oxygen. Zircon forms when hot fluid molten rock or magma cools down and becomes a solid igneous rock. Although pure zircon consists entirely of zirconium, silicon, and oxygen, when the mineral forms, it will usually take up other elements along the way, like lead and uranium. We call these sorts of elements trace elements because they are present in low or trace amounts, measured in parts per million. Although only one or a few atoms in every million may be lead or uranium, we can still measure their concentrations with a mass spec. Importantly, the amount of trace elements in zircon does not change after it forms. The atoms are locked in place until the mineral melts back down into magma. So we can measure the amounts of parent and daughter isotopes like uranium-238 and lead-206 and determine how many half-lives have passed since the formation of the zircon. It's precisely this method that we can use to date the ages of granite rocks, which contain zircon. Let's consider an example of absolute dating that you may be more familiar with. Carbon dating involves measurement of carbon-14, the parent isotope, and nitrogen-14, the daughter isotope. Carbon dating is possible on our planet because virtually all carbon-14 atoms on Earth are produced in the atmosphere as a result of reactions between high-energy cosmic rays and the nitrogen gas that makes up our air. This carbon-14 reacts with oxygen to produce radioactive carbon dioxide. The carbon atom in this carbon dioxide is carbon-14. It makes its way into the food web through plants that use carbon dioxide in photosynthesis to make their own food. It then gets passed up the food chain by herbivores that eat the plants and carnivores that eat the herbivores. The organisms keep acquiring carbon-14 throughout their lives. But once they die, their remains, wood or bones, gain no additional carbon-14. At this point, carbon-14 can only be lost from those remains through radioactive decay. So absolute ages can be determined from the remains by looking at the concentrations of carbon-14 and nitrogen-14. Overall, absolute dating methods like these produce consistent and reliable results. And improvements to technology continue to improve our ability to determine the ages of minerals, rocks, fossils, and sediment on Earth, and beyond. So, what is the exact age of our planet, and how do we know? Scientists have rigorously pursued this question, analyzing every conceivable type of sample. Although much of the results are subject to debate, here's what we know. The oldest rock on Earth, perhaps, may be the Acosta gneiss, located in the Northwest Territories of Canada, where it is exposed on an island about 300 kilometers north of Yellowknife. It is a metamorphic rock that was produced from metamorphism of an older igneous rock. The dating of zircon in this rock indicates that it is roughly 4 billion years old. Although other rocks on Earth may be older, we have the most confidence in the age of this one. What about the oldest mineral? The oldest mineral, we think, not surprisingly, is a zircon crystal from the Jack Hills of Western Australia. Geochemical analysis suggests that this crystal may be 4.4 billion years old. Surprisingly, however, we may learn about the age of our planet by looking beyond it. Although the moon landing mission only managed to return a small and precious amount of moon rock, these rocks have been intensely studied. The oldest dated moon rocks are between 4.4 and 4.5 billion years old, suggesting that our nearest planetary neighbor is about that age. Because it's safe to assume that the Earth and Moon probably formed around the same time, in one respect or another, its rocks give us one more clue as to the age of our planet. Our last big resource for studying the age of our world and the solar system as a whole is meteorites. With some exceptions, the majority of the meteorites in our solar system likely formed around the same time as the sun and planets. They represent the leftovers. Dozens of meteorites have been analyzed using absolute dating methods, and the results indicate that they are all generally between 4.53 and 4.58 billion years old. Altogether, absolute dating tells us that the Earth is over 4.5 billion years old and gives us the tools needed to figure out the timing of all of the other major events in Earth history.